Good morning and welcome to COE 3001, Mechanics of Deformable Bodies. My name is Yazuo Lu and I will be your instructor this semester. I want to begin this course by setting expectations clearly and explaining why this subject matters, not only for this semester, but for your entire engineering education. Many of you are coming into this class with a very practical mindset. You may be wondering how grades are determined, how heavy the workload will be, and whether this course will be manageable alongside your other classes. These are completely reasonable concerns. Engineering curricula are demanding, and success requires careful planning. My goal today is to remove uncertainty as early as possible so that you know exactly what is expected of you and how to succeed. Beyond the logistics, I want to emphasize something more fundamental. This course is not just another requirement on your degree checklist. Mechanics of deformable bodies is one of the core pillars of engineering analysis. Whether you go into mechanical, civil, aerospace, or biomedical engineering, the ideas you learn here will reappear again and again, sometimes explicitly, sometimes implicitly, but always critically. At its heart, this course addresses a simple but profound question. What happens to real materials and structures when forces are applied? Not just whether forces balance, as in statics, but how objects stretch, bend, twist, and sometimes fail. Understanding that response is what allows engineers to design structures that are safe, efficient, and reliable. At the beginning of this course, we will go through the syllabus. First, the basics. All lecture notes, assignments, and solutions will be posted on Canvas. Canvas should be your primary reference for everything related to this course. I will hold in-person office hours during the week in MRDC 4114A, which is located next to the meeting room. I will also offer online office hours by appointment. Please think of office hour not as a resort, but as a normal part of your learning process. Mechanics is cumulative, and small gaps can grow quickly if left unattended. This course builds directly on two prerequisites, statics and differential equations. From statics, you should be comfortable with free body diagrams and equilibrium equations. From differential equations, you should be comfortable with derivatives, integrals, and boundary value problems. If either of these feels rusty, reviewing them early will significantly reduce the frustration later in this semester. Our textbook is Mechanics of Materials by Gear and Goodnow, 9th edition. Although I specify the version, other editions are totally fine. When I assign homework, I will provide the full problem context, so you won't be lost if you have a different version of the textbook. Okay, let's talk about grades. Here's a breakdown. First, the attendance. The attendance is not required but recommended. We will do 3 random attendance checks this semester. If you present once, you will get 1 bonus point, twice 3 points, and all 3 times you will get full 6 points. I know some of you may thinking that why bother with the attendance points? Well, let me tell you. In my experience, students who attend the class regularly typically perform significantly better than exams. Plus, there's valuable materials we discuss in class that isn't in the textbook. There will be 6 homework assignments, each worth 6 points. Your lowest homework grade will be dropped, meaning that effectively there are 5 assignments. The policy is designed to give you flexibility and room to improve. Well, typed homework summation earns a 1-point bonus per assignment, up to a maximum of 4 bonus points. This is intentional. Students are expected to communicate technical work clearly and professionally, and learning to type-side equations is a valuable long-term skill. There will be a midterm exam and a final exam, both in class and closed book. You are allowed 1 letter-sized equation sheet, double-sided. Copying homework solutions onto the equation sheet is prohibited. The equation sheet is meant to support understanding, not to replace your understanding. Well, the final grades are assigned based on absolute thresholds. Although we may curve the midterm and final exam score, the total score will not be curved. If everyone earns an A, everyone receives an A. The grading scale is transparent, and success is achievable with constant effort. You are permitted to use generative AI tools to specify concepts, review materials, or explore alternative explanations. However, using AI to complete homework or submitting AI-generated work as your own is strictly prohibited and constitutes academic misconduct. Think of AI as an learning aid, not a decision maker. Engineers requires judgment, and judgment cannot be outsourced. Over-reliance on AI without understanding will harm your exam performance and your ability to apply mechanics in real situations. Before moving on, let me briefly go over the course principles because they define how we learn and how we maintain fairness in this class. Discussion on homework problems and lecture notes is strongly encouraged. Talking through ideas, asking questions, and helping each other understand concepts are all part of effective learning. However, the exchange of written solutions or completed work is not permitted. Your submitted work must always reflect your own understanding. Unless prior approval is granted, late assignments will receive a 30% penalty. In addition, assignments submitted after solutions has been posted will not be accepted. Well, another thing is, unless approval is granted, no makeup exams will be given. Exams are designed to assess individual understanding at a specific point in time, and maintaining uniform conditions is essential. By the end of this course, you should be able to analyze three fundamental aspects of structural behavior. First, the strengths. Strength refers to the ability of a structure to resist load without fail. It answers the question, how much load can this structure carry before something breaks? Stiffness refers to the stability to resist deformation, even if a structure doesn't break. Excessive deformation may render it unusable. Many engineering designs are governed by stiffness rather than the strength. Stability refers to the ability of a structure to maintain equilibrium without a sudden collapse. Buckling failures can occur even when stresses are relatively low, making stability one of the most dangerous failure modes. COE 3001 sits between statics and more advanced courses such as machine design, elasticity, plasticity, fracture mechanics, and fatigue. Statics taught you how to compute forces. This course teaches you how those forces deform materials. Later course will build on this foundation to study more complex material behavior and failure mechanisms. The structure of this course follows a deliberate progression. We begin with axial members or bars subject to tension and compression. These problems are conceptually simple and allow us to introduce stress, strain, and constitutive relations. We then move to the shafts under torsion, where rotational deformation becomes important. Next, we study the beams under bending, which form the backbone of most structural systems. Finally, we examine columns and buckling, where stability rather than strength govern failure. If some of these ideas feel abstract at the first, that is completely normal. This slide shows the overall roadmap of the course. At first glance, it may look complicated, and that is completely okay. You are not expected to understand all of this right now. The purpose of the figure is not to detail but structure. The course starts with basic deformation modes such as tension, compression, shear, bending, and torsion. From there, we learn how to compute the internal forces inside a structure, and then translate these internal forces into stresses. Once we understand stress, the course naturally branches into three major directions. One branch focuses on strength, asking whether a structure will fail. Another focused on stiffness, asking whether the deformation is acceptable. The third focused on stability, asking whether the structure can suddenly lose equilibrium, such as through buckling. Although in the course the topics are connected, some problems can be solved using simple methods early on, while others require more advanced tools that we will develop later. That is why you may see arrows that go forward then come back. For now, you should think of this figure as a map, not a checklist. As we move through the semester, we will revisit this diagram many times, and each time more of it will start to make sense. Towards the very end of the course, we will briefly introduce commercial engineering software. Just to give you a first impression of a numerical simulation in practice. The image on these slides are examples of what such softwares can do. For example, predicting stress distributions, deformation, and overall structural response in real components and full systems. The purpose is simply to help you connect what you learn analytically in this class with how mechanics is applied in real engineering workflows. Think of this as a preview, not a requirement. For now, we will move on and focus on the fundamentals. The mechanics of materials is the hidden backbone of civilization. I want to share some stories that illustrate the critical importance of mechanics and materials. The Saturn V rocket, which carried astronauts to the moon, experienced enormous mechanical loads. Its structure endured compression from its own weight, tension from engine thrust, bending from aerodynamic forces, and torsion from control systems. The primary challenge was not material strength alone, but structural stiffness and stability. Thin-walled shells had to be light enough to fly, yet stiff enough to avoid buckling. At the opposite extreme is the bathyscaphe Trieste, which descended to the deepest point in the ocean. Its spherical steel pressure hull was designed to withstand approximately 110 megapascals of external water pressure. The spherical geometry ensured uniform compressive stress, demonstrating how geometry can be just as important as material selection. The Statue of Liberty presents another fascinating case. Its wrought iron frame supports the copper skin. Here's the clever part. The copper shell expands and contracts with temperature changes, while the iron framework resists deformation. The central pylon handles compression. To support the vertical load, armature bars provide tension to prevent collapse from wind or weight, and the wind loads, especially on the torch arm, create bending and torsion forces. This engineering solution allows the copper skin to move independently while keeping the statue standing upright. Without understanding these deformation principles, Lady Liberty might have collapsed long ago. Now let's look at what happens when we get it wrong. The Tacoma Narrows Bridge, which opened on July 1, 1940, dramatically collapsed into Puget Sound just 4 months later on November 7th. At the time, it was the longest suspension bridge of its kind. The collapse resulted from design faults that didn't properly account for aerodynamic forces and the bridge's natural frequency. The violent swaying and eventual collapse tragically resulted in the death of a Cocker Spaniel named Toby. This incident revolutionized bridge design and taught engineers critical lessons about resonance and structural dynamics. Similarly, Aloha Airlines Flight 243 in 1988 suffered catastrophic failure due to fatigue cracks and poor maintenance. A large section of the roof tore off mid-flight, consisting of the entire top half of the aircraft skin from behind the cockpit to the fore-wing area. This explosive decompression and resulted in one fatality, flight attendant Clarabelle C.B. Lansing, who was ejected from the plane, and injured 65 others. This tragedy highlighted the importance of understanding fatigue failure in materials. These examples aren't just history lessons. They are powerful reminders of why COE 3001 matters. Mechanics of deformable bodies is foundational across biomedical, mechanical, civil, and aerospace engineering. It explores how materials respond to external forces, addressing the central question: how do materials resist or fail under external load? This brings us back to the three critical properties of this course: strength, the capacity of a structure to resist loads; stiffness, the ability to resist changes in shape; stability, the ability to resist buckling under compressive stresses. Now let's get into the technical part of our course. In statics, you worked primarily with rigid bodies, but in the real world everything deforms under load. That's where deformable bodies comes in. A rigid body is an idealized model. It is assumed to sustain unbounded load without any changes in shape or size. No matter how large the applied force are, the geometry of the body remains unchanged. Because of this assumption, rigid body mechanics focus only on overall loading carry, kinematics, and dynamics, without concern for internal deformation. This is the framework you primarily used in Theory 2001, statics. In contrast, a deformable body is a more realistic representation of real materials. For deformable bodies, an upper bound on load exists. When forces are applied, the body experiences change in shape and size. These deformations may be small or large, but they cannot be ignored. As a result, deformable body mechanics cares not only about equilibrium, but also about how the structure deforms during or due to loading. To analyze deformable bodies, we rely on several idealizations that work well at the macroscopic scale. First, we assume materials are continuous, meaning we ignore voids, cracks, and defects. Second, we assume materials are homogeneous, with uniform properties throughout the body. Third, we often assume materials are isotropic, behaving identically in all directions. These assumptions are not strictly true at the microscopic or atomic scale, as shown in the image on the right. However, when we study engineering scale structures such as beams, columns, this idealization provides accurate and practical results. The key idea is to always think about the length scale you are interested in. At the scale of this course, these assumptions are both reasonable and extremely useful. In mechanics, isotropic means that material has the same mechanical properties in all directions. In other words, its response doesn't depend on orientation. Many common engineering materials such as metals and glass can often be treated as isotropic at the macroscopic scale. This assumption greatly simplifies analysis and works well for most problems in this course. In contrast, anisotropic materials have direction-dependent properties. Examples include composites and materials like wood, where the mechanical response depends strongly on direction. In Theory 3001, we will mostly assume materials are isotropic unless stated otherwise. Before we can analyze deformations, we need a common language, and the language is mathematics. Let's review some fundamental concepts. First, units. In this course, we will use the SI units consistently. That means length is measured in meters, mass in kilograms, force in newtons, moments in newton meters, and energy in joules. You may be familiar with US customary units from previous courses, but for this class, all analysis and final answers are recommended to express in SI units. Using a single, consistent unit system helps avoid mistakes and makes equations easier to interpret. Unit convention is your responsibility, so please pay close attention to units throughout your calculations. Because real engineering loads are either very huge or very small, we rarely talk in original SI units. We use prefixes, and you need to be fluent in them. Based on my experience, roughing prefixes during calculation can lead to serious errors in the results, especially when handled with square roots. Here are some examples. Kilo, that is 10 to the power of 3. We often measure force in kilonewtons, right? Second, mega, the capital M, that is 10 to the power of 6. This is standard for stress. If you calculate stress, it will most always be in megapascal. The third one, giga, the capital G, right? This is 10 to the power of 9. This is huge. We usually use this for modulars because metals are incredibly stiff. Here is my advice. Always pay attention to prefixes, because a small mistake can lead to errors for several orders of magnitude. Okay, then we go to the scalars and vectors. A scalar is a quantity that has magnitude only. Examples include mass, time, temperature, and energy. Scalars do not have a direction, so they can be described by a single number with units. A vector, on the other hand, has both magnitudes and direction. Common examples in mechanics include force, velocity, displacement, and acceleration. Because direction matters, vector cannot be treated as ordinary numbers. Vectors are often expressed in component form, such as using I and j in 2 dimensions. Vector addition is performed by adding components, which corresponds to placing 2 vectors head to tail connected. Throughout this course, we will work extensively with vectors, since most mechanical quantities depends not only on how large they are, but also on the direction in which they act. For example, the most common one is force, right? We always care about the direction of force. Understanding vector operation is essential for our work. In mechanics, there are 2 common ways to multiply vectors, the dot product and the cross product. The dot product measures how much one vector acts along the direction of another. It is defined as A dot B equals AB cosine phi, which can be interpreted as the magnitude of A projected onto B, multiplied by the magnitude of B. In component form, the dot product is simply the sum of the products of corresponding components. The cross product, in contrast, produces a new vector that is perpendicular to both input vectors. Its magnitude is AB sine phi, and the direction is determined by the right-hand rule. In this course, the dot product is commonly used to compute components of force and stresses, while the cross product is essential for analyzing moments and torques. In mechanics of deformable bodies, derivatives and differential equations are essential tools, not abstract mathematics. A derivative describes a rate of change. Geometrically, it represents the slope of a curve. Physically, it tells us how a quantity varies with position or time. For example, in structural mechanics, derivatives of displacement describe slope, curvature, and strain. When we analyze real structures, quantities such as stress, strain, and displacement vary continuously along a body. This naturally leads to differential equations, which relate external loads to internal response. Most problems in this course are boundary value problems, where conditions are specified as supports or boundaries, rather than at a single point. Understanding derivatives and differential equations allow us to connect loads, material properties, and geometry to the resulting deformation. You don't need to memorize every formula on these slides. What matters is recognizing that calculus is the language we use to describe how structures deform. Here is a simple reminder of what we mean by a differential equation. A first-order differential equation relates a function to its first derivative, usually written as dy dx equals fxy, right? You may also see this written as y prime equals fxy. These forms are completely equivalent. In this course, however, We will mostly often deal with simpler case where the derivative depends only on the independent variable. For example, dy over dx equals fx. Right? In that case, the solution is obtained by integration. The key takeaway is not the notation, but the idea. Differential equations allow us to describe how physical quantities vary continuously along a structure. This is exactly what we need in mechanics of deformable bodies.